Hi everybody, this is Mr. Backstrom, and today I want to take a look at a problem from section 4.3. This is finding critical points and using the second derivative to find the local maxima and minima of a function here. So here's the function, it's negative e to the x times x minus 7. So with these functions, it's usually a lot easier just to distribute that out because we're going to have to be finding derivatives here. So just distributing that out, you have negative x e to the x, and that's going to be plus 7 e to the x. You could probably do that using the chain rule too, but I like this better. So the first derivative here, applying the product rule, you're going to have the first times the derivative of the second, so that's negative x times e to the x plus the second times the derivative of the first. That's just going to be minus e to the x. And then plus the derivative of 7e to the x is just 7e to the x. 7e to the x. And then that's going to clean up to, let's see, negative, or we could pull out an e to the x, and there's not an x there. We pull out an e to the x, and that'll leave us a negative x, a minus 1 here, and a plus 7 there. Alright, so that is e to the x, and then I think we're going to have a 6 minus x. 6 minus x. Alright, and let's go ahead and work on the second derivative before we really get going any farther. So the second derivative of this is equal to, and I'll use this line to find the second derivative. So once again, we're applying the chain rule, so that's going to be negative x e to the x, because the first times the derivative of the second, plus the second times the derivative of the first, and once again we're going to have the minus 1 times e to the x again, so that's just minus e to the x, and then we're going to have the derivative of minus e to the x, which is just minus e to the x, and then of the plus 7 e to the x, which is just plus 7 e to the x. So we're going to get this, and we can pull out an e to the x, and we're going to get x minus 1 plus 7, or we're going to get e to the x, and it looks like we're going to get 5 minus x there. Alright, so what can we do with all of this mess here? Alright, so the critical points, these are the points that make the first derivative equal to 0. So for the critical points, I'm going to take a look at e to the x times 6 minus x equals 0. Alright, now if we know what the graph of e to the x looks like, we know that the x-axis is actually a horizontal asymptote, so it never actually touches that. So there's no value that we can put in for x to make this value 0 here. So really we're only looking for values to make this 0. So here x is equal to 6 is going to be our only critical value. So this is where this is the only spot that we can have a local minimum or a local maximum. Now, what is that going to be? Well, there's a couple of different ways that we can find out. We can either see whether it's increasing or decreasing when it gets there and when it's leaving there, which is usually what I like to do. But this is asking us to use the second derivative and check the concavity. So let's do that. So if we go to the second function here, and we're going to do e to the x, and then 5 minus x, is we set that one equal to 0. Then what we have here is, once again, the value for that, the inflection point, is going to be x is equal to 5. That's the only thing that's going to make this equal to 0 here. So now we're going to look on both sides of this 5. So got to do a number line here. So I've got my 5 and greater than 5. If I have greater than 5, that's going to make this negative. So 5 minus like 6, that'll be negative. This is going to stay positive, so that'll be negative over here. And if x is less than 5, this will be positive, and this will be positive. So that'll end up being positive. So what does that mean? That means that it is concave up, and then it is concave down. 6, we are concave down. Sorry, really should have said that. So at 6, we're concave down, which makes it a local maximum. A local maximum. Yes. All right. If you have any questions, let me know, and I hope you have a great rest of your day. Thanks.